Good day, everyone. We are Group 3, and today we'll present our research on the topic Enhancing Practical Skills of Industrial Robotics Students Through Competition-Based Learning, an excellent research at Jiangxi Vocational College of Science and Technology. And here are our team members. Our presentation today is divided into 5 parts: Introduction, Methodology, Implementation, Findings and Discussion, and Conclusion. We hope that through these 5 sections, you will gain a clear understanding of our research process. Now let's begin with the introduction. First, let's look at the background. With the rapid development of industrial automation, there has been a continuous increase in demand for highly skilled talent. However, traditional training courses are unable to fully meet industry needs, leaving a significant gap between the skills students acquire and the actual requirements of workplace. Competition-based learning, or we call it CBL, has been gaining attention for its ability to boost students' engagement and practical abilities. Now let's consider the current situation at Jiangxi Vocational College of Science and Technology. The existing training courses do a good job of reinforcing students' basic operational skills, but they fall short in cultivating the flexibility to handle complex tasks and comprehensive practical abilities. Furthermore, team-based tests are shown to be more effective than individual tasks in enhancing students' engagement and teamwork skills. Clearly, the challenge for current training courses is that they focus mainly on basic skill training, with little connection to real-world industrial tasks, making it difficult for students to adapt to actual work environments. Therefore, the core question of our research is the competition-based practical training courses intervention effective in improving students' practical skills? To answer this, we conduct an action research study. From our literature review, we identified 3 key elements that are crucial to enhancing practical skills. The first one is task planning abilities. The second one is execution and adaptability. The last one is teamwork skills. These 3 abilities form the foundation for our teaching intervention, which will be improved through competition-based learning, forming the core framework of our research. Thus, our research aims to achieve 2 main objectives. The first one is to optimize the training course using action research, enhancing students' practical operational skills in the field of industrial robotics. The second one is to assess whether integrating competition-based learning into the training courses significantly impact students' practical abilities, comparing it to traditional teaching method to determine if it offers superior results in developing comprehensive practical skills. Next, let's take a look at the research methodology. We adopted the action research methodology because it aligns closely with the goal of optimizing industrial robotics training. Action research is practice-oriented and follows a plan, act, observe, reflect cyclical model, allowing continuous adjustment and improvement in the course design within a real teaching environment. This methodology enables us to flexibly respond to complex education scenarios by combining classroom observation and student feedback, especially in fostering multidimensional practical skills like task planning, execution, adaptation, and teamwork. It provides a scientific basis for the design and implementation of competition-based training courses and offers ongoing opportunities for improvement. Our research consisted of 2 major loops. We selected 80 students and divided them into two groups. The first one is a regular group, which focused on basic operational training. The second one is the competition group, which engaged in complex tasks that simulated real competition scenarios, emphasizing teamwork and task planning. We collected data through test and service, reflecting on and optimizing the teaching method after each loop. Okay, next, let my teammate Geng Yan to introduce the implementation.
Now, let's dive into the implementation phase, showcasing how competition-based teaching was integrated into the course and highlighting the differences in performance between the two groups. For the first loop, we designed distinct teaching goals, content, and methods for both groups. The teaching intervention in the first loop focused on developing competition-specific skills. Here's how it was structured. Teaching goals: to help students master the skills required for competitions, improve teamwork, and enhance their ability to perform under pressure. Teaching content: we simulated real competition scenario to boost students' problem-solving abilities. Teaching methods: task-driven learning was employed, with a focus on increasing teamwork exercises and simulating high-pressure environments to help students adjust to competition challenges. In the first loop, we performed descriptive statistical analysis on the test results and concluded the following. Regular group scores varied significantly, ranging from 69 to 95. With an average score of 81.695. Competition group scores were more concentrated, with an average score of 95.533, showing overall better performance. In general, the performance of the competition group was notably better and more consistent than that of the regular group. In the normality test for the first loop, the results were as follows. Regular group, group 1, p-values equals 0.388, suggesting data that closely approximates a normal distribution. Competition group, group 2, p-value equals 0.043, indicating a significant deviation in the high score range. From the QQ plot, we observe that the regular group's data aligns closely with the trend line, while the competition group's data deviates significantly at the tail end. To ensure the reliability of our analysis, we decided to use non-parametric methods for subsequent evaluations. As shown in the graph, the p-value is 0.010, which is significantly less than 0.05. This indicates a significant difference between the competition and regular groups. Regular group, group 1, showed a more dispersed score distribution with greater variability. Competition group, group 2, had a more concentrated distribution with more consistent performance. Although the competition group's results were more concentrated, there was still some variability, indicating that there is room for further improvements in reducing score discrepancies. In the first cycle or loop, we also collected feedback from students on task planning, execution, adaptation, and teamwork abilities via a survey. Descriptive statistics of the results showed the following. The competition group outperformed the regular group in all ability indicators. In terms of teamwork ability, the competition group has a standard deviation of 0.44554, indicating higher variability in the development of this ability across students. This suggests that while the competition-based teaching method had a significant overall effect, further optimization is needed in developing teamwork skills. To test the significance of the differences between the two groups, we performed an independent samples t-test on the survey data, and the results were as follows. All ability indicators showed a p-value less than 0.001, indicating highly significant differences. The competition group scored significantly higher than the regular group in the task planning, execution and adaptation, and teamwork abilities. These results indicate that the competition-based teaching has a significant impact on improving students' abilities, especially in developing comprehensive skills. After the first loop, we reflected on the results and reached the following conclusions. Strengths. Students in the competition group showed outstanding performance in task planning and execution, and their overall scores were significantly better than the regular group. Issues. The development of teamwork ability was uneven, with some students participating less, which affected the overall collaboration quality. These reflections provided clear directions for optimization in the second loop, where we aimed to improve task difficulty, time distribution, and collaboration mechanisms. To address the issues identified in the first loop, we revised the teaching plan for the second loop. During the second loop, we implemented interventions in the following three areas: adjusting task difficulty to ensure that students of different skill levels could participate, strengthening teaching work mechanism, ensuring each student had a clear role and responsibility, providing personalized guidance to help students with weaker foundations integrate into the team and improve their performance. In the second loop, we assessed the effectiveness of the optimized teaching approach through the test data. The result showed the competition group's optimized average score significantly improved to 91.625 with a more concentrated score distribution, indicating that most students showed considerable improvement. Compared to the first loop, the optimized competition group performed more evenly across all ability indicators. We conducted a normality test on the second loop's exam data, and the results were as follows. Competition group, first loop, data in the high score range deviated from normal distribution. Shapiro-Wilk p-value equals 0.043, suggesting clear skewness. Competition group second loop optimized data distribution was closer to normal, and the scores were more concentrated, indicating that optimization successfully reduced the score discrepancies. The normality test confirmed that the optimized competition group achieved a more balanced overall performance. After second loop, we performed an independent samples t-test, and the results were as follows. The competition group second loop optimized significantly outperformed both the regular group and the competition group from the first loop. The specific data is as follows. Competition group optimized average score of 91.625, standard deviation of 4.578. Regular group average score of 84.352, standard deviation of 6.132. Competition group first loop average score of 85.533, standard deviation of 5.238. The p-value from the t-test was less than 0.001, confirming that the optimized competition group showed a statistically significant advantages. in performance. In addition to exam data, we conducted a second loop survey, which revealed the competition group optimized outperformed the regular group in all ability indicators, particularly in task planning and teamwork, with more balanced performance in the optimized competition group. Student feedback on the course was positive, with most students finding the optimized course more challenging, while benefiting from increased teamwork opportunities and enhanced task planning skills. We further analyzed the second loop survey data using ANOVA, and the results were as follows. Task planning ability, F value equals 72.094, p-value less than 0.001, indicating significant differences between the three groups in task planning. Execution and adaptation ability, F value equals 82.570, p-value less than 0.001, showing that the optimized competition group significantly outperformed the other two groups in execution and adaptation abilities. Teamwork ability, F value equals 36.563, p-value less than 0.001, demonstrating that the optimized competition group showed a significant improvement in teamwork ability compared to both the first loop's competition group and the regular group. These results show that optimized competition-based teaching method led to significant improvements across all three core skills, particularly in execution, adaptation, and teamwork. After reflecting on the second loop, we reached the following conclusion. The optimized competition-based course effectively enhanced students' overall abilities, particularly in task planning, execution, and adaptation, and teamwork. Data analysis confirmed that optimizing task difficulty, time allocation, and teamwork mechanics led to significant progress in students' score and skill development. However, we still found some variation in teamwork abilities, suggesting that further optimization in task design and support strategies is needed to ensure equal opportunities for all students to grow. My part is over.
Now, let's move on to the fourth section of the presentation, findings and discussion. In this section, we will summarize the key findings from both loops, discuss the effectiveness of competition-based teaching, and identify areas for further optimization. Let's review the result from the first and the second loops to examine the impact of the optimization. In the first loop, the competition group performed much better than the regular group, showing greater accuracy and efficiency. And the competition group showed stronger adaptability, reacting more quickly to unexpected changes in tasks. And while the competition group outperformed the regular group in teamwork, some students still struggled with participation and adaptation. And in the second group, the optimized competition group showed more balanced teamwork and development, with the performance gaps narrowing. As for task problem solving, adjustments in task difficulty, time allocation, and teamwork mechanisms had a noticeable impact, improving problem-solving ability. And students made significant progress in task planning, execution, adoption, and teamwork. In summary, the two loops of research show that competition-based teaching greatly improves students' overall abilities, with even more pronounced effect after the optimization, particularly in teamwork and adaptability. Next, we discuss the key findings of the study in depth, mainly from three aspects: the limitation of traditional vocational education, the advantages of competition-based learning, and the role of inclusive and adaptive task design. Okay, the traditional teaching focuses on basic operations, but has obvious deficiencies in task planning, adaptability, and teamwork. The performance of the regular class verifies this, and the lack of comprehensive ability reflects the limitation of traditional teaching. The combination of task-driven and industrial scenario simulation effectively connects theory and practice. Project-based learning and collaborative learning improve students' adaptability and problem-solving ability. The course design is repeatedly optimized to further improve the teaching effect. As for the role of inclusive and adaptive task design, through differentiated tasks and clear division of labor, students of different levels has improved and narrowed the gap. Reasonable task, complexity, and balanced support strategies ensure the fairness of skill development. These discussions help us better understand the value of competitive teaching and also provide direction for future task design and teaching optimization. Next, we summarized the result of the competition teaching, discuss the challenge encountered, and put forward suggestions for improvement and future research directions. The results show that competitive teaching significantly improves students' abilities in task planning, execution, adaptation, and teamwork. This model provides an innovative and effective path for vocational education, especially in combining practical skills with theoretical knowledge. The improvement effect of the second loop by adjusting the difficulty of tasks, time allocation, and collaboration mechanisms, students' performance has been significantly improved, the skill gap has been narrowed, and the overall balance has been improved. As for the challenges and suggestions, although the collaboration ability of most students has improved, some students still perform poorly. It is recommended to break down tasks into smaller steps and assign appropriate role according to the students' abilities to help students with weaker foundation integrate into the team. And the future research direction is that it's recommended to expand the sample size to verify the applicability to the result in a wider group. Well, in conclusion, the research demonstrates that competition-based teaching method, when carefully optimized, significantly enhance students' abilities in critical areas like task planning, execution, adaptation, and teamwork. The iterative optimization process, combined with targeted interventions and personalized support, lead to substantial improvement in students' performance and engagement. However, ongoing refinements are necessary to ensure that all students, regardless of skill level, have an equal opportunity to develop and succeed in collaborative environments. Okay, our presentation is over. Thank you for your attention.